All right, let's get started. How was your weekend, first off? Good? No complaints? Nothing exceptional either? That's pretty good, actually. That's how weekends are supposed to be. All right, so last time, first things first, this is actually, I've been carrying this book with me for a week, and I keep forgetting to give you a look. So this is a visualization of flows. The book was assembled in the 1980s from a lot of research work that was done in the 60s and 70s on visualizing different types of flows. So I want you to appreciate specifically, we went through the homework and dimensionless groups, and I want you to appreciate Reynolds numbers and what it does for classification of flows. So when we have these different dimensionless groups, we will use for classification, so we model things differently depending on what those parameters are. So if you specifically look at the creeping flow, which is a very low Reynolds number, so a very slow Reynolds number, which is not just velocity. There's velocity, density, body radius or diameter, and viscosity of the fluid all baked in. Right? So we can scale it differently. We see a very orderly situation. And the way this was done was simply by dropping dye into water. And this is in between parallel plates flowing around a small cylinder, right? So everything is in order. There are different types of objects. As you can see, so this was Reynolds number very low. It was less than 1. It was probably even 0.01. Now, as you move up, this is all kinds of different flows, but there is turbulence, something like this. So this is a Reynolds number of 2,000 in a similar situation. I think this was visualized by dropping particles in the fluid, I think. Similar thing, right? So you can see, like in the wake of the object, we have this turbulence, which you know from like boats on a lake or a surface of water, because they're going at very high speed. So just appreciate how these start developing, and this is what we refer to as turbulence, and that's what we use Reynolds number to classify those types of flows. So it's an old book, but it's still a pretty amazing. There's here the green, this first page. So take a look. We also had some severe improving our appreciation of viscosity and how we model it. And specifically for that last time, so our basic Newtonian fluid, which we think water, kind of flows nicely. The moment you apply some shear stress, it's just going to go. It's going to go, and the resistance to flow will remain constant no matter what. That is basically a description of a Newtonian fluid. A lot of fluids that are of interest, specifically industrial fluids, such as drilling fluids, cement slurries, foams, and so forth, they are exhibiting much more complex behavior. And that behavior will change possibly with the applied shear rate. So the faster the velocity and velocity change, right? That will result in different. So if I have velocity gradients, they might affect the flow differently, and the resistance to flow might be different. And for that, we need non-Newtonian behavior. But before we actually go and formalize it, we introduced the definition of so-called shear strain rate, often referred to just as a strain rate or shear rate, gamma. And let me go back to my solid deformation. So we define gamma as if I'm shearing the body as opposed to applying a normal stress to it. Bless you. We need to all say bless you, and maybe it stops. Or maybe it doesn't. He's allergic to shear strain rate. Anyway, shear strain rate is in the air, and it's affecting the health of students. All right. So if you're shearing a body, I'm going to have a delta L in the shear direction. And when I divide that by h, which presumably doesn't change in this simple application, right? Then I'm going to refer to that as shear strain. When I'm looking at its change, so now I'm in a fluid, and I'm looking at its change in time, and we're going to refer to it as gamma dot. Okay, so gamma is the shear strain rate is gamma dot. Then it's a differential in time of delta L over H. H basically gets out of this. I do hope I'm recording in this whole business. I don't have any signs. So delta L over H is my shear. So shear, and H can go out because it doesn't change in time, right? So when I put this, this is essentially a definition of velocity in x direction, right? Changes in my delta L, how much I have actually traversed over this short time period over H. And I can rewrite that. My Vx is basically negative version. So Vx of H is a 0, right? So it's minus 0 minus what my Vx of the lower plate is. And that's basically delta Vx over delta in y direction, which is H. And since that's applicable for any H that I consider, and any type of velocity that I apply, that's essentially the derivative of Vx with respect to y. So my strain rate, so this is change in time, is essentially minus dVx dy. Okay? And this is a spatial gradient, or one of the spatial gradients for velocity Vx. Okay. So then for non-Newtonian fluids, I'm going to have dependence on that shear rate, or rather, for different values of how my gradient of velocity changes, I might have actually different resistance of the fluid, right? And that might increase or decrease my my shear. We had that fun example of a shear thickening fluid when you throw cornstarch in water, right? It's fun to think about, but basically there's this complex starch molecules that are way larger than anything that we think about, like little balls bouncing around and interacting. So their interaction is complex. In particular, as you pound them really quickly, you will quickly expel fluid from them and suddenly it's going to solidify. Whereas if you go slowly, it's still liquefied, right? So it basically acts like water mostly, which it mostly is at that rate, right? So there is different behavior in those cases. I could also change in time. I showed this last time. So this is the awkward plot. We typically plot versus shear rate, not in time, but here, different shear rates, different curves are actually for different shear rates. Basically, over time, I might have differences in shear stresses for these different shear rates applied. So different behavior, both versus shear rate and versus time. Okay. One of these complex fluids, so now I'm going to basically list the number of models, okay, that we apply, is Bingham plastic. So conceptually or mathematically, if you think about a Newtonian fluid, there's one parameter that describes the fluid, viscosity, and it's constant. It doesn't change. So basically, as we increase complexity, we will increase the number of parameters that I'm using in the model. Okay? In this particular model, I'm saying, okay, if my shear stress is high enough, so if I have enough shear stress of the system, then I'm going to technically behave as a viscous fluid. But until then, I'm not moving. That's your toothpaste, okay, or ketchup. Ketchup, when flipped over, doesn't just flow. You need to kind of shake it, and that's essentially you of that shear stress. And that parameter that becomes a parameter in my mathematical description of it, tau 0, is called yield stress. Happy enough, to yield and start flowing. And after you do, you have this minus mu 0 dx dy that is awfully similar to my Newtonian fluid. So what describes this fluid is tau 0 and mu 0. What makes this a little complicated when dealing with it mathematically and trying to solve for analytical solutions is that you have to treat these two differently. And when getting and solving for the equations, you actually don't know whether you're in this regime or that regime. So you have to solve for them separately and kind of merge them together. And at all times, there might be a case that shear stress is something that dynamically develops in my fluid, and it might fall below of this tau 0, and then you simply say, well, I'm just going to go with inertia. I'm just going to go with whatever was there. Okay, my Bx will not change after that point. Okay, so this is how idealized Bingham plastic looks like. So you essentially, if it wasn't a Bingham plastic, you would go through 0. Because for 0 shear stress, there would be nothing happening. And here I need something tau 0, which is basically the intercept here. So it's my shifted. I like to think about it as a shifted Newtonian fluid behavior. Now, I'm going to get that slide at the very end, but basically viscosimeters are how we measure viscosity in the lab. They go over a range of shear rates. And for every shear rate, they measure effective viscosity at that rate. Stabilize the rate, and so you get different points on the Wilkins curve. And the homework that is assigned today, there will be a lot of, this is basically going to be a bunch of curve fitting exercises of you feeding experimental measurements on this viscosity to different models. Okay? So this is ideas of Bingham. Now, what makes a fluid a Bingham fluid is that we have a crystal-like arrangement of some particles in there. So it could be basically solid particles. And this crystal structure in itself kind of resists any kind of movement if I have a low shear stress. And at higher stresses, it breaks down. And then the thing starts flowing. And after that, it flows kind of normally with constant resistance. And this is how it looks like in practice. We're going to go get to solving these, but just now accept that this is a standard profile, velocity profile, or all the Newtonian fluid. Actually, this is a cross-section for the second two. So that's why I have R versus Z. So this is a classical parabolic distribution of velocities, 0 at the wall, maximum in the middle. And in between a parabola. Now, if you have a Bingham, you're going to start having something like this. So shear stress in itself is maximized on the wall and minimum at this point. Makes sense that the really is minimum of the parabola, right? So it's basically 0 here and maximum in absolute value on the wall. And somewhere in between there, I'm crossing this tau 0, the yield stress. Okay? So if you imagine that that cross is right here at this radius, right? Beyond that, you have a parabolic behavior of a Newtonian fluid, and until there is just inertia, you're just dragging everybody. You're essentially dragging with this velocity, you're dragging everybody else. So you have this profile that is sort of like flattened. Does that make sense? Any sense? Based on the formula I showed? Let's go. So I'm saying that if I don't have shear stress that is high enough, I'm just saying that my velocity gradient is 0. So that's what I mean by inertia. Whatever is my neighbor that has enough shear stress to win, that's what I'm going to be moving with. Basically, I'm dragging that point. And that's essentially what's going on here, which is like a solid behavior, right? Solid just goes, all of it. So this is transition from fluid to solid behavior. And those were just the formulas that I showed that describe that. and balancing the actual physical behavior with the formulas is that's the whole art of this course. Okay? And it's not an easy balance, so don't give yourself help. Now we move to shear thinning or thickening fluids. Those are so-called power law fluids. I think grammatically I'm missing a dash between power law. So basically with increasing and decreasing shear stress, I might have different behavior. So my viscosity, my resistance to flow might get less as I'm increasing the shear rate. Or it could get higher. So a very common model for this is a two-parameter model. This is my shear rate, remember? Got that? And I'm taking absolute value because when it's negative, I'm just taking the value of it, right? So it's always a positive number. And basically parameters are m and n. Now if my n is equal to 0, then this will be 1, correct? Yes. So I'm going to collapse back to Newtonian fluid. Minus m, but this used to be m. And we're just writing m, sometimes it's also k, simply to differentiate it from the regular viscosity. But what's really now my Newtonian viscosity, because I have this dvx, dvi still, dy sitting here, basically this is my viscosity, okay? So my viscosity, which I'm now going to, again, just to change labels so that we are not equating, I'm going to use eta. My non-Newtonian viscosity, eta, is this m times shear rate, which is absolute dvx dy, to the n minus 1. So my viscosity depends. It's a function of shear rate. It used to be constant. It used to be just m, right? And that was Newtonian behavior. And I still get that, but when I plug in n is equal to 1 here. However, now it depends on it. How does it depend? When my n is less than 1, with the larger shear rate, I actually had diminishing because I'm raising it to the power to say, it becomes 1 over something, right? Something that is large, and that basically diminishes it. So my effective viscosity reduces as I increase the shear rate. And that's shear thinning behavior. Sometimes it's also called pseudoplastic. Blood behaves that way. Blood has platelets. At larger shear rates, they align, and they're actually easier to fold. And at slower shear rates, they're kind of moving in all kinds of directions, and some of them might be orthogonal to each other, for instance. And that creates larger resistance. Does that make sense? Foam is also often shear thinning. Foam is bubbles. Those bubbles could change size and higher shear rates, and as they change size, they're going to change the viscosity. The foam resistance depends, so foam has a lot of little interfaces inside of those bubbles, and that's what provides resistance. The smaller the bubbles, the more resistance. The larger the bubbles, the less resistance, because with the smaller and smaller bubbles, I have more area of those. Okay? That's shear thinning. Sometimes a lot of gels. I'm doing this because I'm thinking of hairstyle gel. Not sure. Does anybody use it? I sometimes do, but very rarely. But basically, when you apply it, it's very thick, right? If you actually want to do something with it, you do this. But it's high shear rate. Also increasing a little bit of temperature too, right? So that's high shear rate. So as you shear it, it somehow eases it up, and then you apply it to your hair. Right? So that's shear thinning behavior. Shear thickening or dilating, that could be the cornstarch or sand suspension, but you will see sand suspension to be an example for everything, from Bingham plastic to shear thinning to shear thickening. Depends on the sand, depends on what else we add to it, so don't be confused by that. So basically that means with the high shear rate, something rearranges. It's typically these complex objects within. It could be particulates, it could be large molecules, it could be whatever it is that I have in my fluid, or combination of them all. And basically they start providing more resistance. They don't align, they mess up. And as they mess up or build up, they're gonna provide more resistance, and we call that shear thickening or dilatant fluid. And different ends model that. And the way we get ends and ends, so I have two parameters by curve fitting, two experimental data. So what makes it, I already went over that. So when I have a Newtonian fluid, my molecule is a very small molecule, say 100-ish angstroms. And the origin of viscosity is this exchange of like molecules bouncing into each other, right? That's basically the mechanism. Now, when I have these complex molecules, polymer chains could be 10 centimeters. That's long. And they're also long in one direction, not in the others, right? Or I could have in blood, I have platelets. They're so longish in two directions, but not in one of them. And that starts creating different types of resistance. They get entangled. Okay, I'm going to possibly overshare. But we constantly have, because of my long hair, clogging in the bathroom. But it's not just my long hair. My theory is that my long hair would just elongate and grow if you actually flush it down. The problem is that everybody else in the house has short hair. So when you combine the two, there's an entanglement, then you get this thickening within the pipes, and we have to actually go within in there and fish it out. No Drano helps at that point. You actually have to just pull it up. Okay? And this is like, so it depends what's in there. And if you have different agents, then they will have different sizes, different objects of different sizes, different shapes. Will entangle, and you might get actually shear thickening behavior. Okay? So it depends what does that particular combination do. If it actually aligns and untangles at high shear rates, then it's going to go faster. If it tangles up and gets more complex, it's going to go slower, and that we basically modify viscosity with that into model. So in summary, what you have as shear stress versus, so this was my basic Newtonian behavior, straight line for different, so basically it's my model for viscosity based on parallel plates is tau Ix is minus viscosity times dx dy. And the dx dy is my shear stress. So shear stress and shear strain are linearly related for Newtonian fluid. Simply the slope is my viscosity. Do we see that? It's a simple linear relationship. When I look at the shear stress versus shear strain plot, I'm going to get its slope, and this slope for a line is always constant, and I'm going to through the zero, so I only really have just that slope that describes the behavior. When we get to Bingham fluid, I have this yield stress. So for anything to start happening, I have to have a tau 0 here, which is my intercept. And this is my line. So this is still a straight line. If I'm curve fitting, it's a linear regression. Remember that term? So I'm fitting two parameters in the simplest of the possible models, and that is a straight line. Now, what happens for this red curve here? I hope you see red. Okay? So here, slope is this. It's a derivative, right? So it's nonlinear slope. Right? And that nonlinear slope is captured by this m shear rate to n minus 1. So this is my m gamma dot to n minus 1, right? This is gamma dot. So essentially here I have a slope, this slope, and here my slope is a little flatter, so lesser, right? So my slope with increase in the shear rate my slope gets lesser, right? And that is shear thinning. Whereas this flip side is the opposite, this pink, magenta, whatever the term for it is. Okay? So basically, as I go with the increased shear rate, my slope gets steeper and steeper, so it's larger, right? The slope of the line here is larger than it is here, and that's shear thickening behavior. So if I kind of give you something like this, you'll be able to recognize this in basic models. Yeah? Okay. Excellent. Well, you would think that that would be all, but it's not that simple. Most of the water-based cement slurries and most of the water-based drilling fluids, they do exhibit Bingham plastic behavior. However, sometimes you will hear that the aqueous suspension, even in these slides, you will find examples with these suspensions of particles. They might include drilling fluids or cement slurries. They might be just suspensions of particles, are Bingham plastic, and sometimes it's a power law fluid. And that's because of all kinds of additives that we actually might have to keep those slurries moving and suspended. And those additives might include clays. Clays, first thing, they have very strong surface forces, and they will align with each other. They will hydrate and expand. So you can see how that can actually, so they will basically create aggregates as they hydrate. And that will change the behavior of the fluid, and also at different shear rates. Barite might be added, particles of variable sizes. I might have sand of a range of sizes. No sand comes perfectly cut into the size, especially the less money you pay for it. Polymers, you might have different types of gels within the fluid. Whatever it is that was added to the fluid, all those intermolecular collisions become complex, and they differ for different velocity or velocity gradients. And here's an example where we need to predict how things will behave if we inject the cement slurry until it sets. It's typically described as a Bingham plastic. So we need two parameters to describe it, because we want to figure out how it's going to behave and how fast will it take to actually fill our casing geometries, right? All right. So we might have different behaviors at different shear rates or in time. And what you do in practice, you find the best model for the relevant range of shear stresses. So if you're filling annulus of certain size, or typically pumping at a certain rate, that gives you, or the range of rates, range of annulus, and this is where the equations that we're going to develop later will help. You can basically then predict, well, what is going to be the range of shear rates. So you go to viscosimeter and you measure that range of shear rates, and that's the part that you fix to a model that you need. And that might change, so I can actually show you example. This is an example from Bingham plastic, from some of the older. This is the paper that actually had a title something like what yield stress? There's no such thing as perfectly defined yield stress, because depending at the range, so here you're looking at shear rates from 0 to 6 hertz, second to the minus 1. And here from 0 to 160. And if you fit only these 4 points that are basically only here, right, then you're going to get a different yield stress. Yield stress here is just below 6. And this one is 9.5. So it could be 5 versus 9.5 in yield stress, depending on what is the range of points you put together. So this is where you're going to ask yourself, and as an engineer, well, what is the shear rate range that is actually applicable for the application I have? And that might differ from going through the wellbore, going through the annulus, going through perforations. In all of those cases, you're going to have different shear stresses. Actually, before this, let's actually see. So there are these videos. I would like to go back to them. It's called rheological behavior of fluids, and let me go with Bingham first. So it says go there, and you can play them. So let me introduce these videos first. They're very old, 1965. But if you go to the web page of the videos, there's actually an entire, it used to be a National Committee for Fluid Mechanics films that was in 60s. And the videos are very dated. However, you will see the style of the delivery, the way it was recorded, it's dated. However, it's the most complete set that hasn't been repeated since. You can find on YouTube quite a bit of everything, right? But this was curated and on a pretty high level in terms of quality, regardless of the delivery being sort of more of a 1965 compared to the today. There is definite difference. So here you can behave. So there's actually one on rheological behavior. There's different ones, like flow visualization. One is an interesting one to watch. You can actually pick and choose here, even like magnetic fluids. So there's different types of visualizations and talks. But we're going to just quickly go through this rheological behavior of fluids. And it says that well, I'll just play the first 4 minutes because I think this is where we get the...
Rheology, in its broadest sense, is a study of the relationship between force and deformation in continuous media. In this film, we shall focus our attention on fluids. We have marked a portion of a flow field outside the viscous boundary layer. Here, water behaves almost like an inviscid fluid. In the model of the inviscid fluid, the basic assumption behind the stress-deformation relation, whether the fluid is equilibrium or in motion, is that there are no shear stresses, or, equivalently, that the pressure is isotropic. This statement, when combined with the balance of momentum equation, leads to Euler's equation of motion. In this flow, glycerin shows evidence of shear stresses. Water and glycerin are two of many fluids that behave in a manner called Newtonian. With no relative motion, the Newtonian fluid has no shear stresses. The pressure is isotropic. In relative motion, however, the stresses are linear functions of the instantaneous velocity gradients. If we formulate this stress-deformation relation for the Newtonian fluid so that it is independent of the observer and couple it with momentum equations, we obtain the Navier-Stokes equation. There are many situations, however, for which these models are quite inadequate. This is especially the case when you are dealing with materials containing large molecules. This ball, for example, bounces quite vigorously, like an elastic solid. Yet, it really is a fluid. We'll come back to it later. Here's a viscous material, which I can pour into this beaker. No, I think I'll use this beaker instead. I can even cut it to length. This material is a solution of a high polymer. Some other materials that do not follow the simple Newtonian model are molten plastics, egg white, paint, and mayonnaise. Mayonnaise holds its shape if you let it alone, yet it spreads with ease. Here is a more controllable experiment illustrating the same phenomenon. There is no stopcock at the bottom, and this vessel is open to the atmosphere on top, and yet this clay suspension does not flow. I can put this simple piston here, place this small weight on it, still no flow. Now a larger weight. It flows, but very slowly. A much larger weight. The flow is fairly rapid. I take the weight off. The flow stops. In a state of equilibrium, this material can support a shearing stress up to a critical value called a yield value. Even with materials not having yield values.
So this is basically the simple part, like of the another way you can play the whole thing yourself, but I just wanted to give example of how Bingham plastics look like. Okay. And again, you can see that the delivery is dated to 1965, but it's excellent content. So. And very comprehensive, which is rare. YouTube gives these glimpses, right? That can be great, individual glimpses, but not necessarily comprehensively going over all types of behavior. Okay. And there is actually, I might speed up. So it says there is examples of shear, thinning, and thickening at 12 minutes. So I'm going to go there to the 12 minutes. I'm going to play that part. Oops, I overshoot. All right, somewhere here.
Constant. These are two identical burettes containing the same Newtonian fluid. The pressure head in one is twice that in the other. The ratio of rates of flow is also 2 to 1, as we expect from Poisson's law. But if we charge both burettes with the fluid exhibiting nonlinear behavior and apply the same ratio of pressure heads, the result is quite different. With this polymer solution, when the head is doubled, the rate of flow is more than doubled. It appears that the viscosity is less at the higher velocity gradient.
Double the rate.
This type of steady flow behavior is called pseudoplastic or shear thinning. There are some fluids that create a contrary situation. For this suspension, the viscosity is higher at the higher rates of flow. This is called dilatant or shear thickening behavior. In the steady laminar flow of incompressible Newtonian fluids.
So I'm going to stop it. You can, this is just to exemplify some of these behaviors in a more sort of a measured way. You can watch the whole thing. It's interesting. Or I would think so, but I would think so. So. Okay. So let's just move on. So these were examples of the power fluid. I said, oh, okay, it's not that simple. These are examples of power law fluid. And see that this is an aqueous suspension of solid particles as well. Not sure which type of solid particles. And each curve is a different concentration of those particles. So as you increase the concentration of these solid particles, you get different behaviors versus shear rate. So this is this and different. This is actually measuring viscosity. Kind of nearly constant, especially for these high shear rates for the concentration of 60, but it changes with shear rate, the effective viscosity for higher. Okay. So it increases. So this would be a shear thickening. So you do have to be a little careful on what is plot. Most commonly, you will see shear stress versus shear strain rate, right? So that's basically tau yx versus gamma dot, right? But sometimes it's going to plot viscosity or something else, or time. Okay? So the person who plots decides what they plot. Okay. Let's now combine some of them, because as I said, it's not necessarily simple. And as we combine, we're going to fit more parameters, really. Okay? So here's Herschel-Bulkley model. It's a combination of power law. So this was written separately. So basically, this first part is the power law, and then tau 0 over gamma dot. You can also think about this as a tau 0 times gamma dot. And viscosity is presumed infinite at less than yield stress tau 0. So how many parameters do you have in this one? N tau 0. And this is your effective viscosity as a function of shear rate with 3 parameters. Yes? So this is Herschel-Bulkley. Again, it's a combination, so it exhibits a little bit of yield stress behavior as well as the power law. And this is how the plot would look like. So you can see yield stress, you can recognize here like what's happening at 0. And when you look at 0, if you have a non-zero shear stress, well, that's your yield stress behavior right there. After that, it's not a straight line like a Bingham plastic. It's something more complicated. It depends on the shear rate that you have. And in this particular plot, what happens to the shear rate? So at lower shear rates, this is my slope, right? My effective viscosity. And at higher shear rate, the slope is less steep. So if my slope decreases with higher shear rate, what type of behavior do I have here plot? Shear thinning, okay, thins out. So lower slope is less viscosity. Viscosity is the slope. Effective viscosity is the slope. So basically this N here was the shear thinning end, right? Not the shear thickening one. Okay. There's another Sisko model. Looks a little simpler. It's also 3 parameters. So now I have just this effective viscosity, eta infinity, that I approach as my rate increases. So this is your eta 0. And in between, I have a power law. Okay. So how many parameters am I fitting here? 3. M and eta 0. It's, again, all about having a functional relationship that you fit into. And then this one tends to fit the most behaviors, actually, especially over a very high range of shear rates. But I have to fit how many parameters do we see here? Let's count. Eta infinity, so that's my viscosity. Constant viscosity is for super large shear rates. This is my eta 0 right here, plateaus. Eta 0 is right here, very close to 0. I have another plateau. So those are 2 viscosities at 2 different limits. Okay. In between, I have essentially a power law. Okay. And that power law happens to have lambda and m in there. A type of power law, right? So that's a cross model. So how many do we count parameters? 4. So with larger complexity, you introduce more parameters to fit. You can always introduce more complexity into your models. Question is, what do you get in return, and do they actually then work better over a larger range, right? If you're just working in a certain range like here, well, don't go to that model. It's overdoing things, right? But that depends on the application. So we have different models that fit different applications. And this one fits rather well over a range. So this is different fitting cross model, our experimental data. So this is a solution of polyacrylamide, blood, xanthan gum, latex. So now I'm telling you that all of these fluids, like blood or this is a xanthan gum, is typically used in EOR applications as a common polymer. Now I'm telling you that all of these are cross model. Before that, I told you that they're power law fluids, right? Well, they are power law. There's a range of shear rates where they are fitting power law really well, right? So that's this like flexibility. Even when you tell them for the most part this is for the power law, or for the most part it's a Bingham plastic, those are basically the two models that for certain range of applications are working. But that said, it's never super simple, and depending on the different shear rate ranges, you might pick a different model. So just be sensitive to that. So this is an example for a shear thinning fluid. Example of fitting. So data is in dots. Okay? And this is what different models, how well you can fit them. So this is a power law. And in this range, not bad, right? Actually, everything is relatively okay in this range, right? But then here, so this cross model kind of captures this limiting behavior at the low and high viscosity. One example might be also what is happening to this. Well, it's always basically the case. What is happening to the complex fluid? So in certain cases, the fluid might separate or fall apart at higher shear stress or lower shear stress, and that gives you these limiting behaviors. So here it's well put together and high resistance, but then it kind of falls apart or aligns or whatever at the very low viscosity at high shear rates, and that's basically that plateau here that we see. Okay. All right. So it can get even more complex. We're not going to model it as a more complex, but technically there are time-dependent fluids. They will start as one type of behavior, but over time they will change to the other. I just want you to know, so this effective velocity depends on shear rate, but not itself on a shear rate and time, and how long. So there's certain history that builds up, right, in the fluid. That behavior definitely happens, especially when you have clay in the system. But we typically then like just at the earlier time fitting one power law model, and a later time another, or something of that sort. And that's how we're actually capturing this behavior. All of this stuff of application, if you think about cement slurry, well, it settles, it becomes solid, right? So once your cement settles, it's not even fluid anymore. So there's definitely time-different behavior. But you're hopefully operating within the time limit of that cement slurry being a slurry, and that's what you're modeling with your flow model, and then you let it be, and it settles, and you have cement casing finished, right? So those are like something to be sensitive about, but we're not going to work with time-dependent fluids. This is for your knowledge. So I have thixotropic and rheopeptic. All right. So this I actually mentioned already. How do we measure viscosity? We're going to get back to this when we actually calculate. So this is my little parallel plate model. You can't do infinite parallel plates. That would be required for developing this in practical measurements. What we actually do is a very thin cylinder, and then you kind of zoom into So mentioned here, if it's a very low curvature, you could actually get parallel plates. So most viscosimeters are this, there's a fixed cylinder in the middle and a rotating one on the outside. And basically that approximates approximate planar geometry that gives me equations that I can fit to. And that's how we measure effective viscosity. Okay? And regardless of this, all of these single points on the plots that you see are basically this effective viscosity at a given shear rate. So that effective viscosity might change, and when you fit it, we get those more complex behaviors that I pointed out. Okay? All right. I will stop here. Apologies for going overboard by 3 minutes. All right.